Hey everyone, welcome back to AP Precalc. This is lesson 3.9. Let's get right into it. All right, so here's a bell ringer for today. Pause the video if you haven't done this yet because I am about to go over the answers. All right, so for the first one here, this may seem like a new type of problem. We have a polynomial function x or negative x squared times x minus 2 times x plus 3, and we want to see where is this less than or equal to 0. And so while this may look new, it really isn't because this is a rational inequality just where the denominator is 1. And so what we want to do here is find the critical values first. And so we want to see wherever the numerator or denominator is equal to 0. From the numerator, we should have 0, 2, and negative 3. From the denominator, it's because it's just 1. We don't have any there this time. Now we're going to plot all three of those numbers on a number line. So let's do that now. So we got negative 3, you got 0, positive 2. And now we need to determine if each number will get an open or a closed circle. So remember, any number that comes from the denominator is going to be an open circle automatically. Any number that comes from the numerator, which in this case is all three of them, is going to be dependent on this sign there. And because it's less than or equal to, and it has that equal to underline, they are going to be all closed circles. So let's give those all closed circle there, and a closed circle for 2. If it was just less than and not less than or equal to, it would be all open circles there. Now what we want to do is, I'll switch colors for this one. We will now test 4 numbers in each interval. So one that's less than negative 3 will go negative 4. One that's between negative 3 and 0, that should be maybe negative 1, positive 1 here, positive 3 there. And we're going to plug them into this equation and see if we get a number that's less than or equal to 0. But the main thing is we are not really as concerned about the exact value of the number as we are, is it basically going to be positive or negative, right? And it's always going to be less than or equal to 0 in any type of question that you may be asked. So for this one here, let's start with 3, right? Negative 3 squared is negative 9. That's a negative number. 3 minus 2 is 1. That's positive. And then 3 plus 3 is 6. That is also positive. A positive times a negative will give us a negative number, which is less than 0. That's a good thing. So we're going to represent this area with a check mark. Doing it pretty quickly for the other 3 now. 1 squared is 1 times negative 1 is negative. 1 minus 2 is negative. 1 plus 3 is a positive number. Here, this would give us a positive number, which is not less than 0. So this is going to be an x, negative 1. This should be negative times a positive. This will also give us a positive, which is not less than 0. So this is going to be an x. And then negative 4, we have a negative number times a negative number times negative 4 plus 3 is negative 1. That's another negative number. 3 negatives will give us a negative, which is less than 0. So that is going to be a check mark. And so with that being said now, our rational inequality will contain negative 3 and any values less than that, or any values greater than 2. So our answer should be B. This is this inequality in interval notation. So from negative infinity to negative 3, union 2 to infinity. You could also say, if you got to write your own answer, x is less than negative 3 or equal to, and x is greater or equal to 2. Here, we are missing something though, so B is correct. However, you would also include the value of 0 in your solution set because 0 is filled in, so that would also be a value that would make the equation true. That was a mistake in the answer key there. All right, so number 2 here, we are looking at a residual plot for a linear regression model. Remember, this is not a plot of the actual data, but a plot of how far off we are from our line of best fit. Now, the only thing we care about with residual plots is there a pattern? Here, there is no pattern that I see. The patterns will be very clear if there is one, and so 3 examples that I've seen on AP exams have been like that, like this, or just like a straight line, right? Very clear and obvious patterns. There's no pattern here. So that means the model would be appropriate. So the linear model is a good thing. So here the linear model is appropriate because there is no pattern. C would be the best answer here. All right, number 3. Here we want to find the value of a and d given this cosine function. So here, let's start with d, our midline. We have a maximum at 4, and then we have a minimum at -8. And so the distance between this is 12. Half of that should be 6. And then 6 down from +4 will be -2. So that should be our midline here. That looks like a midline visually, and so d is going to be -2. So let's mark that to start. Now we just need to figure out our a value. And so our a value is going to be our amplitude, either positive or negative, and that's the key here. Our amplitude is 6. That's the distance from the maximum to the midline. So it's going to be a 6. Now, is it going to be positive or negative? Here we see that there is no horizontal translation, right? We're not moving the graph left or right on the inside. We do have a b value, but that's not important. So we are going to start the graph at 0, and at 0 we are starting at a minimum going up, which means we should have a negative cosine graph. So a should be -6, not +6. A lot of people missed that on the last test. So we have -2 times -6. We should get +12 as our answer for C. All right, so today we're going to be talking about inverse trig functions and inverse operations. So let's identify the inverse operations of each of these real quick. The inverse operation of addition is subtraction, because an inverse operation is basically what undoes the mess that an operation like addition does, and we would use subtraction here. So let me write that in. For multiplication, the inverse operation is division. Here you would divide both sides by 3 to solve for x. For cubing, to undo that, we are going to do the cube root. There's really not a fancy name for this, so it's literally just cube root. And then trig, how do we solve for x? We are going to use something called inverse trig. So I know, really fancy name, but that is the name for what we're going to talk about today. So talking about inverse trig, right? On your last quiz with the unit circle, I asked you what is sine of pi over 6, let's say. And you would tell me that it was 1/2. Here we were doing sine of an angle on the inside, and you gave me the y value, the output, which was a trig value. Now we're going to be defining the inverse function of this, which, remember, the inverse function is when you switch x and y. And so here, if we were to find the inverse function of sine, we would say sine to the power of -1. This is not actually to the power of -1, it's just how we write the notation of inverse sine of 1/2 equals pi over 6. So this is the inverse sine of a trig value equals an angle measure. An equivalent way to say this is if I say arc sine of 1/2 equals pi over 6. This is the same thing because arc sine and sine to the power of -1, or inverse sine, are going to be synonymous. They mean the exact same thing. There is no difference between them. So the way we're going to write all the inverse trig is for sine, the inverse of that is going to be either inverse sine or arc sine. For cosine, the inverse of that will be inverse cosine or arc cosine. And then for tangent, the inverse of this would be inverse tangent or arctan. Right? So the difference between these two is none. There's no difference between them. You will see them used interchangeably in problems, so be prepared to work with both different types there. All right, so example number 1, I kind of already did this, but let's do it again. Write the statement sine of pi over 6 equals 1/2 in an equivalent form using arc sine notation. So here, if I do the inverse sine and now I'm going to have the trig value on the inside equals an angle measure, pi over 6, or the equivalent would be arc sine of 1/2, let me erase that, equals pi over 6. These two are the exact same, so there's no difference between those two, but these are both an equivalent way to write that equation right there. All right, so quick, is this graph invertible? Does this graph have an inverse function? Is it 1-to-1? And the answer here is no. No, it does not, right? That graph, which if you looked closely, was actually the graph of sine of x. Sine of x is not invertible, right? And this is going way, way back to lesson 2.8 inverse functions, but it's not invertible because it does not pass the horizontal line test, right? Actually, every single point will break the horizontal line test that you can think of. And so, as a result, just the general graph of sine of x does not have an inverse function. And so how the flip can we take sine of x and make that whole function an inverse function, right? We can't have inverse sine of x if this isn't even a function, right? Then it's not an inverse function, duh. And so the way we're going to do this is actually by cutting the graph down and restricting the domains. And so I'm going to show you what I mean by that. Whenever we're talking about inverse sine, if we have this graph right here, like that. This is a graph of sine of x. What we're going to do is we are almost going to erase the graph and get rid of those parts right there and only look when we're talking about inverse sine or arc sine. We are only going to talk about it from negative pi over 2 to pi over 2 right here. If we only look at this and erase the rest of this graph, here, this now becomes invertible, right? It passes the horizontal line test everywhere. And it contains every value from 1 to -1, so our range is covered there. And so this is going to be the new domain of sine when dealing with inverse trig there. For cosine, it's going to be very similar, so let me draw this one out again. Like that. We are going to erase part of this graph, like so, and only look at it from 0 to pi, right? We could have gone from negative pi to 0, but mathematicians just kind of settled on 0 to pi. It's a lot easier, right? More angles that we're familiar with. So our domain for cosine is going to be from 0 to pi there, and this is also invertible, right? Passes the horizontal line test, and so that is the domain for cosine. And for tangent, it's pretty easy as well. We are just going to restrict the domain to one period of tangent. Here, we're going from negative pi over 2 to pi over 2, right, like that. This will cover every y value possible, but also be invertible, where it will always pass the horizontal line test. Now, remember, sine and arcsine are inverse functions, so they'll cancel each other out. So just like if you have the square root of, let's say, x, and then we square this, the square root and the square will cancel out, and you're just left with x. Very similar here. If you have inverse sine of sine, you can cancel those out, and that is just equal to pi over 3, right? That angle inside. All right, so now here's an important note about inverse trig functions. This is a slide I would commit to memory when talking about the range of these inverse trig functions. So here for sine, right, the two quadrants we're going to work with are these two quadrants right here, the first and the fourth quadrant. Now this is where a lot of people get mixed up. This is going from negative pi over 2 to pi over 2. So if I ask about this angle right here, let's say this is a perfect 45 degrees, right? Just to create a really nice example. In terms of radians, I would say this angle measure is pi over 4. Now think about this in your head. If I ask for this angle measure right here, what would that angle measure be? And I bet a lot of you guys would want to say 7 pi over 4. That would actually be wrong. And the reason why is because we're going to want to say negative pi over 4. It's important to note here that you're actually only looking at angles from negative 90 degrees to 90 degrees, right? If we look at it in terms of degrees. And so if we said 7 pi over 4 or 315 degrees, right, that's not falling in that range. Instead, we need to use the same coterminal angle and say negative 45 degrees. So here, let me show this here. A lot of you guys are saying this angle, but instead we're going to use the equivalent coterminal angle and just say negative pi over 4 instead of 7 pi over 4 when we're talking about inverse trig, and especially just the fourth quadrant in particular. Right, if we take a look at cosine, cosine is going to be the first two quadrants. Here, it's all positive, so this is pi over 4 if it's another 45-degree angle. And if this was 45 degrees as well, this would be 3 pi over 4. So that doesn't change. For tangent, though, tangent's domain or inverse tangent's range is going to be, if we do another 45-degree angle, this would be pi over 4, easy, first quadrant. But this would also be negative pi over 4, right? Because we're going from negative pi over 2 to pi over 2. Now, the only difference between sine and tangent is they're pretty much the same, except tangent, we don't include the values of pi over 2 and negative pi over 2, just because at those exact values, tangent is undefined with those vertical asymptotes. So that is how the range is a little different for inverse tangent there. All right, example number 2, evaluate the following expressions. So let's work through these three together. First, we have inverse cosine of a trig value. And so we're going to want an angle measure as a result. So cosine of what angle basically gives us negative root 2 over 2. That's the question I'm asking myself. Now think about the domain for cosine. It's going to be the first two quadrants shaded. The first quadrant, cosine is positive. In the second quadrant, cosine is negative, right, with all students take calculus. And I see a negative trig value. So I'm probably going to be looking for an angle in the second quadrant. Once we have this is actually a perfect 45-degree angle again. So this should be 3 pi over 4. So that should be our answer to 2a. I'm going to put 3 pi over 4. All right, now we have inverse sine of negative root 3 over 2. Remembering the domain for inverse sine, that's going to be the first and fourth quadrant. In the first quadrant, sine is positive. In the fourth one, though, sine is negative. And so, negative root 3 over 2, using the unit circle, I know that is a 60-degree reference angle in the second quadrant. So it should be right here. But instead of saying 5 pi over 3, that most people would want to, that's wrong. Instead, we're going to say negative pi over 3 or negative 60 degrees. I want all angle measures in radians though. So negative pi over 3 should be our answer for that one. Now finally, we have inverse tangent of positive root 3. Remember, the domain for tangent is going to be pretty much the same as sine. Here, tangent's positive. In the fourth quadrant, tangent is negative. Tangent equals positive root 3 at a 60-degree reference angle. So that's going to be pi over 3. And it should just be the positive value because here it's positive root 3. So pi over 3 should be our answer there. All right, let's move on. Here, you're going to see a few of these on your next quiz where it's two equations. To solve it, just set them equal to each other. So we have, let's see, 12 inverse cosine of x equals 2 pi. What we're going to do first is divide just both sides by 12. The reason we do this is because you want to isolate this, the inverse trig function, to just get it by itself on one side. So here we will be left with inverse cosine of x and equals pi over 6 there. That's 2 pi over 12 simplified. Now what we can actually do to both sides is we can, to get rid of the inverse cosine and just have x, we can take cosine of both sides. There. Once we have that, the cosine and the inverse cosine will cancel out, and that's what I was saying before about them canceling each other out to just give us x. and then x equals, and cosine of pi over 6 from the unit circle should just be positive root 3 over 2. And so this should be our answer here for example number 3. Example number 4, we have 2 arc cosine or inverse cosine of x equals pi. I would start by dividing both sides by 2. Here we just have arc cosine of x equals pi over 2. And then here I'm going to take cosine of both sides, cancel those out to just give us x equals cosine pi over 2. And then from the unit circle, you should get x to be equal to 0 because that is the trig value of cosine pi over 2. All right, example 5. We have inverse cosine of 4x equals 2 pi over 3. And so here we don't have anything that we have to deal with, so we can just start by taking cosine of both sides. And we should get 4x equals cosine 2 pi over 3. This is going to be, remember, if you don't have your unit circle, 2 pi over 3 is right here. That's a 60-degree reference angle. Cosine of 60 degrees is 1/2, but it's in the second quadrant, so it should be negative 1/2. And then divide both sides by 4. When working with fractions, I like to think of that as the same as multiplying by 1/4. That way, you just have x equals negative 1/8 as your answer for example 5. Example 6, we have 18 arctan root 3x equals 6 pi. It is important to note here that the radical does extend over the x because with these questions, and you may see this on a AP test or quiz, or AP test or one of my tests or quizzes, here root 3x, where the x is under the radical, is very different than root 3 times x, where x is on the outside of the radical, right? So here x is underneath, so just make sure you keep that and you don't switch it up halfway through. Divide both sides by 18 to get arctan root 3x equals pi over 3. Then I will take tangent of both sides. And then we should get root 3x equals tangent of pi over 3. That, from the unit circle, is just root 3. Here, then, I would square both sides to just get 3x equals 3. So the squares and the square roots will cancel out. Divide both sides by 3 to get x equals 1. So that should be our answer for example 6. Example 7, with these, you just want to do it one at a time. So inverse cosine of sine of 5 pi over 3 is, we want to evaluate the inside first and work from the inside out. So sine of 5 pi over 3 is from the unit circle. 5 pi over 3 is right here. This should be the inverse cosine of negative root 3 over 2. And now we're doing the inverse cosine of negative root 3 over 2. Remember, the domain for cosine is the first two quadrants here. And so it is going to be in the second quadrant. And cosine is equal to negative root 3 over 2 at a 60 degree, or at a 30 degree reference angle. So this should be 5 pi over 6. And that should be our answer C here. All right, number 8, this is probably going to be one of the harder problems you'll see. 1 over pi inverse sine of square root of 3x equals 1/4. Here, I'm going to multiply both sides by 4. I'm going to multiply both sides by pi. You should just get inverse sine root 3x with the x underneath equals pi over 4. Then I'm going to take sine of both sides to get rid of those there. Then we should be left with root 3x equals sine of pi over 4. This is from the unit circle, positive root 2 over 2. I'm going to square both sides to just get 3x equals the square of root 2 is 2 over 2 squared is 4, which is 1/2. Knowing now 3x equals 1/2 here, I am going to divide both sides by 3 to get x equals 1/6 as our answer for example 8. All right, if you guys have any questions, please come see me in office hours, and I will see you guys later. Thanks.